So this section, we're going to talk about sample space and probability. So we're getting into a little less algebraic work, solving equations, doing all that stuff, and more interesting, fun activities where we're going to be rolling dice, flipping coins, looking at cards, finding the probability of something happening. But before we start that, we're going to talk about sample space and how do we determine the probability of these events that are occurring. So first off, the probability of an event is the likelihood that it is going to happen. Most people know of probability from gambling. It's also used a lot in weather, right? So if you have a 100% chance of rain, you know it's going to rain. If you have a 12% chance of rain, it might not rain. So it just depends on the likelihood. And we have this scale that determines that. 0%, not going to happen. 100%, pretty certain it's going to happen. Now you can see these in either numeric whole number form, fractional form, or percentage. Most of the time we're going to use percentages, but you can have probability in any of those cases. We're going to start by talking about sample spaces. So a sample space is all of the outcomes that could possibly happen. So a probability, again, is the likelihood of an event. So some action or trial or something that you're doing or observing, and all the possibilities that could happen from it. Those are your outcomes. So for example, if we have a dice, if I have a dice here, the dice has a probability, has a sample space of 6. 1, 2, 3, 4, 5, and 6. So the collection of one or more events, such as if I roll this dice and I get an odd number, such as 3, that could be however many times that could happen. 1 out of the 6 possibilities. And that would be the outcome of the event, which could be found in the sample space that is listed. And we're going to start by doing a couple of different explorations where we're going to create some sample spaces and then build our way up into those events and those probabilities of them. So the first one, flipping a coin. Everyone's flipped a coin before, right? So you have your coin. We know one side is heads, the other side is tails. So in this case, if I have 3 coins that are flipping, we want to list the possibility of the sample space of the experiment. So when I flip it once, maybe I get heads. I'm going to flip it again, I get tails. That's only on one coin though. If I'm looking at tossing 3 coins all together, I'm going to have a possibility of a larger sample space than just heads or tails, because maybe the first one came heads, the second one came tails, and the third one was tails. It could be any possibility. So the answer to that is first coin, heads or tails. Second coin, heads or tails. Third coin, heads or tails. But it builds off the other possibilities. So if my first coin landed heads, then my second coin landed heads. My third coin could also land heads. So that is one possibility of the sample space. Maybe it went heads, heads, tails. That's a second possibility. And you can see all the different breakdowns of that. And this is actually called a tree diagram. It's branching off each piece. And that is one way that you can come out with the sample space. Now, in order to help you determine, well, how much sample space should I be looking for, we use this multiplicity idea. I know that coin 1 had 2, coin 2 had 2, and coin 3 also has 2. If I multiply all those together, I have a possibility of 8. That is how many would fit in my sample space, right? And I say that down here. Coin 1 has 2 possible outcomes. Coin 2 has 2 possible outcomes. Coin 3 has 2 possible outcomes. So altogether, that makes 8 possible outcomes. And I can count 1, 2, 3, 4, 5, 6, 7. And there's an 8 underneath that one. There's my sample space. So now I just verified how many I actually counted is what it should be because of the multiplicity of it. Okay, next one, rolling dice, right? So again, back to this. I have 1 6-sided dice, and then I have 2 6-sided dice. We want to talk about the sample space of that. Well, 1 6-sided dice has one set of sample space. You could land on 1, you can land on 2, you can land on 3, 4, 5, 6. That's it. It's only options. But if I have 2 dice now, if I roll the first one, I get a 1, The second one could be a 1, 2, 3, 4, 5, or 6. I can roll a 2 the first time and have a possibility of a 1, 2, 3, 4, 5, or 6. So that kind of makes it a little bit bigger, right? And again, if we go with the idea of one dice had 6 outcomes, a second dice had 6 outcomes. If I multiply those, I know I'm going to end up with 36 possibilities. And here are those possibilities. I'm going to move my face over. So again, here's my first possibility. I'm showing you in numbers and dice format. And down here for part B are 2 dice. I said there's 36 of them. Again, you can look at it in the physical dice format or in the numbers. Like I said, if I roll a 1 the first time, I could have 1 and 1. I could have 1 and 2, 1 and 3, so forth. I could have 2 and 1, 2 and 2, 2 and 3, so forth. And that comes up with 36 possibilities. And this is my sample space. And knowing my sample space will help me then if I ask you something like, what is the probability of rolling doubles, right? A double is the same number. So I can see there's the 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. I can see the doubles. I can see how many there are out of the total sample space and then easily answer any questions I ask of you. Okay. The next one is a spinner. You might have seen that before, right? Or if you've ever seen Wheel of Fortune, the big spinner, right? The big wheel there. So this one says, how many ways can you spin a 1? So you look at the wheel. There's only one of them. That's the only possibility. How many ways can you spin a 2? Okay, well, I have 1, 2. I have 2 2s. So there's 2 possibilities for that one. 3, you would count your 3s. Same thing for 4 and 5. For part B, your sample space, well, your sample space is all of the spaces. How many spaces are there? What are they? That's your sample space. And then the total number of outcomes would be how much did you list in your sample space? And this would be your answer, right? So a 1 can only be spun once. 2 was twice. 3 was 3 times. 4 was twice. And 5 was 4 times. That's how many times they appeared in the wheel. There's my sample space. I chose to list them in order. You could list them as you see them around the circle as well. And again, there's 12 outcomes. There was 12 spaces on the spinner and 12 number outcomes listed in my possibility. Okay. The next one, our bag of balls, right, to pull from. So I don't have balls, but I have numbers in circles. These are going to pretend to be the balls that are in the bags. Okay. So as we do this, I'm going to talk about what's happening. First off, notice they're numbered. So I have ball 1, I have ball 2. Okay, and all the red ones are also numbered. That's important. That means order is going to matter. So when it says, how many ways can you choose 2 blue balls? So if all I focus on are these 2, I can pick ball 1 first and then ball 2. That's one way. What if I pick ball 2? Well, now I got ball 2 and then ball 1 I can choose from. That's a second way. So there's only 2 possibilities for that one. For the red, then blue. Okay, so I'm going to put all my reds first. I can pick red 1 and blue 1. I could pick red 1 and blue 2, right? Well, I can do that for all numbers of red. I can pick ball 2 red and blue 1. Red 2, blue 2. I can move on to 3. Red 3, blue 1, red 3, blue 2. And if I go through that, that means every red had 2 possibilities for the blues, right? Every red, I could pick ball 1 for blue and ball 2 for blue. So if everyone had 2 possibilities, that makes 10 total. If I flip it the other way, if I pick the blues first, so if I pick blue number 1, then I can pick red number 1, blue number 1, red number 2, blue number 1, red number 3. I can do the same thing for red 4 and red 5. So that meant blue 1 had 5 possibilities for the red to be attached to it. Same thing's going to happen once I do red 2. Still have 5 red balls I can pull and attach to that. So again, that makes 10 total for choosing a blue first, then a red. Now with the red, we got a little bit more happening here. I have red 1. If I pick red 1 first, then I can pick red 2, red 3, red 4, or red 5 after that. So that was one possibility with 4 red left over because the 1 red was already gone, right? I took this one out of the 5 options. So 1 red with 2, 3, 4, or 5 red chosen after. So that's another 4. And if I was to repeat that with all 5 red numbers, and I could pick red 2 and have red 1, red 3, red 4, red 5. Can't repeat that. I already have it. That's another 1 red with 4 possibilities. There are 5 red total. Each would have 4 possibilities. 5 times 4 means there's 20 possible outcomes. The sample space is everything that I was just kind of explaining to you. So I'm just going to show it. Here's your sample space. There's the blues we talked about, pulling them first. Then we had if I pulled a blue first and then a red, if I pulled a red first and then a blue, and then I have my reds underneath that. That gives me with 42 possible outcomes. All right. So again, as you go through that, it's important that you know how many options. So I knew I had 2 for the blue, plus the 10 for the red, then blue, plus another 10 for the blue, then red, plus another 20 for the red and red. That gets me 42. So when I start listing all of them, I could count it, make sure I have 42 there. Okay. Whew. All right. That was a lot of colors to pull from. Now, once we know sample space, we can start finding theoretical probability. So theoretical probability is when you're looking for a specific event of a favorable outcome. So when all things are equally likely to happen, meaning on a coin, it is equally likely to have it heads versus tails. On a dice, it's equally likely to have it 1, 2, 3, 4, or 5, or 6. Okay, as long as we know how equally it will be, we can find the theoretical probability. Is the number of favorable outcomes out of the possible outcomes. So again, if I have this dice and I roll it and I want to get a 2, there's only 1 2 on this. That's the favorable outcome. One of those 2s out of the 6 possibilities. So it'd be a 1/6 theoretical probability. For the coin, if I want to know it's going to land on heads, there's only 1 head on this coin and there's 2 sides. So it'd be 1 out of 2 or 50%. That is theoretical probability. Oops. So what we can do here, and we'll do this one in class, is this one is not talking about heads or tails or rolling a dice. We're talking about probabilities of picking true or false questions out of however many questions that you have. So we'll work together to come up with a sample space. Knowing true and false means there's 2 outcomes, right? Or 2 possible outcomes. It's either true, it's either false. We look at the whole test all together, and we'll be able to find the probability from there. Okay. Complement. The complement of events, we use this A bar. It's A with a bar over it. Not hard to remember, right? Sometimes people call it A hat because it looks like it has a hat on there. So A bar is the complement, meaning if I know the probability of one event, I want to figure out the probability of it not being that event, I can subtract from the whole. So again, going back to that dice, if I know rolling a 2 is a 1/6, and I want to know, well, what's the complement of it? What's of not rolling a 2? Well, then it would be 1 minus 1/6 or 5/6. Now that's a very small, easy one to figure out. But I also give you an idea of one with larger sample spaces, right? If I have 1 through 100, that's 100 possible outcomes. We want the probability of choosing a number that's 10 or above. Well, if I know there's 10 below it, right, I can figure out by subtracting the whole from the complement of it, what is not that value. We don't often always use complements. Sometimes it's easier just to find the actual event, but they're there. And it's something that you do need to be aware of. So if we have all these, we want to find the complement of it, you're simply going to subtract it from one, from a whole. And if we take a look at, like, for instance, we have them in decimal form, fraction form, whole numbers, could be percentages, just could be anything. You just subtract it from the whole value. Again, we'll walk through this one. We have our large sample space of the 2 dice we've talked about before. And we'll talk about how to do it both ways, how to do it normally and using the complement to find those probabilities. Okay, next thing we're going to talk about is experimental probabilities. So an experimental probability is different than theoretical. Theoretical is what should happen. So when I flip a coin, it should be 50%, 50-50, one half. However, if we actually flip a coin, you're not going to get one half. I promise you that. If you flip a coin, it is very rare that you are going to end up flipping it with a perfect 50%. Now, the more times you do an experiment, the more times it will happen to get closer to the theoretical. However, experiments could be anything. You could flip a coin looking for heads and never get one. Just depends on how you flip it. A whole bunch of other outliers could affect your experiment. So an experimental probability is just basically the number of successes, meaning how many times did it actually happen. So again, if I'm trying to flip a coin and get heads, how many heads did occur out of how many times I did something? How many times did I do the trial of flipping the coin? And that would be your probability of the experiment. Now, granted, all of these are fractions. You could divide them to get the decimals, and then to make it a percent, you times it by 100. So just be aware of that, and it's your choice how you want to leave your probability. Okay, and again, we'll go through an experiment like this where there's your results. I already tell you, you don't have to worry about spinning a spinner. Those are your results. We're going to compare them to theoretically what should happen, because theoretically it looks like everything's a quarter, but what did it actually appear to be? So we're going to learn to compare theoretical to experiments as well. Okay, we're going to look at how to figure out probability from a bar graph. We should know how to read bar graphs. This one's nice. It tells us the events, how many occur. And you just need to know, well, what's the total of it to find the probability of maybe someone owning a dog or a fish or whatever it is asking of you. And the last thing we're going to take a look at is geometric probability. So geometric probability is basically calculating a ratio, making a fraction of the part you're looking at divided by the whole entire thing. So when we do this, it might look like maybe a bullseye, right? Maybe you only want to figure out the inner percentage. If maybe you're throwing darts, right? The dartboard. If you want to get a bullseye in there, what's the probability of hitting that small centerpiece as opposed to the whole entire thing? So it's the part over the whole. And again, if you want to make it a percentage, you times it by 100. I've also given you some basic areas and volume formulas. The probability of the geometric probability can be based off of side lengths or radians, could be area, volume, perimeter, could be anything geometric, any piece of it. Just make sure if you're looking at an area of one figure that you're taking over the area of another of the whole. Don't do an area and a volume. Don't do a length and an area. Don't do parts. Everything, your top and the bottom, should be the same way of solving. So again, if I'm doing area, make sure I have area on the bottom. Volume, volume. A length, a length. And again, like I said, with the bullseye question, with the dartboard, we're going to take a look at things like that. So in this case, I'm not going to go through the whole problem with you, but let's say I want to know what is the probability of scoring a 10-point toss. So I would figure out the area of this inside circle compared to the area of the whole entire square that it's sitting in, and then find the probability of that. Divide the numbers, get the percentage, or leave it as the fraction. If I only want to find the 2-point, so this kind of yellowish ring right here, That means you might have to do something like find the area of that ring, of the larger ring, and then take out those middle pieces because I don't want the 5 or 10. So I got to take those areas away to get my numerator. And then again, still divide by the whole thing, which is the square that it's sitting in. Okay. And again, we'll be working through these together. Just be aware of those geometric formulas that I gave you on the previous side.